My report named grant small spaces based on the Calderon construction. It allows that many operators of null such as Hilbert operators or hard-related operators of maximal function are bounded in the Lebesgue LP space for P in 1 infinity, but aren't bounded in L1 or L infinity. Obtained extrapolation theorem is one on direction the extremal space in which the operator is bounded. The first extrapolation theorems for estimation operators in neighborhood of L infinity proposed by Teichmann and Zygmunt, and corresponding theorem for estimating operators in neighborhood of L1 proposed by Yan. Similar situation in the embedding theorem for Sobolev spaces for the limiting exponent. This theorem led the emergence of extrapolation theory. Classical statement of problems in extrapolation theory have the form problem 1 and problem 2. We illustrate problem 1 and problem 2 with two examples. Usually by LP, we denote the Lebesgue space on the cube. M is maximal hard-related operator defined by formula. We put BP equal LP, Xi of P norm M from LP to L1. Then we arrive at problem with Xi of P approx 1 over P minus 1. If is a Hilbert operator by formula and BP LP and CP is norm Hilbert operator from L infinity to LP, then we arrive at problem 2 with CP equal with CP approx P. The Teichmann-Zygmunt theorem and its generation are relevant to problems on this kind. The description of extremal space given by following theorem. Theorem 1. Bmax is sum of the space B beta from collection with norm. The minimal space B mean in problem 2 is the space B mean is intersection the space B beta from collection with norm. Therefore, one of the main problems of extrapolation theory is calculation of the space B max or B min. This is a difficult problem, and there are only a few classes in its exact solution. Usually, instead, the space B mix or B min type approximation are used. Another approach the problems of extrapolation theorem is the construction of space B beta for the study of basis operators. This is how the grand and small Lebesgue space arise. My report will contain new construction of collection beta and B beta. We present main properties, new grand and small spaces. Preliminary information. Let S of mu is space of measure function, and let G of D stand for characteristic function of D. We can be measure mu also discrete. We need the description of ideal Banach spaces. The definition of ideal Banach spaces See at the board. Let V is white. We denote by symbol XV a new yellow Banach space in which the norm given by the equality. For every ideal space, the associated ideal space X prime consists of an integral functionals. The norm in which is defined by equation. If measure is discrete, then integral must be replaced by a sum. The construction of Calderon play key role in my report. We recall the definition of construction of Calderon. Look on the screen. The Calderon construction has found many applications in the theory of ideal spaces, the theory of prediction of linear operators, in the geometric theory of Banach space. If x1 equals L infinity, then the space phi theta will be denoted by x theta 0. If we put x1 equals L1, we denote the space phi theta by x theta 1. We give a classical example of computing the construction of Calderon for Lebesgue space with white. Example 1. Space x theta 1 and x theta 0 are the main object of my research in my report. Mutual embeddings of space x theta. The monotonicity of embedding space play a key role in the construction of grand and small classical Lebesgue spaces. The following theorem gives necessary Sapiens condition for the monotonicity of space x theta 0 with respect theta. Theorem 2. Look at the screen. This theorem has an important corollary, which says that the norm of space x theta 0 for different theta are not equivalent, or x theta 0 coincide with the space L infinity. Corollary 1. Similar facts are true for construction x theta 1. We give exact formulation of propositions. Theorem 3 is analog theorem 2. In the next session, we define grand and small spaces based on the Calderon construction. Grand and small spaces based on the scale x theta 0. Потише?
Это ирония. Я еле слышу, а кто лучше?
Сюда говорить?
Просто громче.
Хорошо. Well, will a sum that L infinity subset X. L infinity unequal X holds. If X subset L infinity, X unequal L infinity, the correspondence of grand and small space are similar. Еще тише стало. We define grand and small spaces. Definition 2. Definition 2 is the definition of grand spaces. The grand spaces is intersection of x theta 0 the function zeta of alpha play a key role in the construction of the grand space. After logarithm, the equality xi zeta of alpha equal alpha power gamma more 0. Now we give dual definition. Definition 3. The definition 3 is the definition of small space. The small space is sum of the space x theta 0 from collection. The function xi of beta play a key role on the construction of the small spaces. After logarithm, the equality xi beta equal beta power minus gamma more 0. The following theorem shows that terms grand and small are justified. Theorem 2 play a key role in the proof of this theorem. These facts are now for classical grand and small Lebesgue spaces. Theorem 4. In the following theorem, we give an exact description of associative spaces to grand and small spaces. This description gives a complete answer to question posed in the paper of Monica Singh in the journal Positivity. Theorem 5. The associative space for grand space is the small space. The associative space for the small space is the grand space. Grand and small spaces based on the scales x theta 1 have similar properties to grand and small spaces based on the scale x theta 0. Below, we assume that x subset L1, x unequal L1 is true. Here are the exact definition of mathematical object we consider. definition 4. The definition 4 is the definition the ground space. The definition 5 is the definition the small space. The ground space is the intersection of the space x theta 1 from collection, and the small space is the sum of spaces x theta 1 of collection. Main properties of ground small spaces based on the scales x theta 1 are quite similar to properties of ground small spaces based on the scales x theta 0. Theorem 6 and theorem 7. The theorem 7 gives the description of the associative spaces for grand and small spaces. We give some examples to illustrate our construction. Example 1. The Lebesgue space LP and small LP. Let omega subset Rn and the Lebesgue measure mu be given. Put x LP of omega. The condition LP subset LP, L infinity subset LP is satisfied if only if measure of omega less infinity. Our construction obtain classical grand and small Lebesgue spaces in this case. Let V be white, but X LP V. Our construction obtain nucleus of grand and small Lebesgue spaces with white in this case. Let Sn is the space of one side sequence with coordinate convergence. Let X LP small. Our construction obtain classical grand and small Lebesgue space in this case. Let X LP V. Our construction obtain nucleus of grand and small Lebesgue space of sequence with white in this case. Let measure omega equal infinity, but x L infinity V0 intersection LP V1. If this space subset L infinity of omega, then the construction from section 1.2 to obtain the construction grand and small space Lebesgue spaces for measure omega equal infinity. We need just to watch the monotonicity of embeddings. But x equal L1 W0 plus LP W1 of omega. If L1 a subset of this space, then construction from section 1.3 to obtain another construction grand and small Lebesgue space for measure omega equal infinity. Example 2. The symmetric space of function. In this section, we will demonstrate our general construction for symmetric space. For definities, we will consider symmetric function space on the z omega of Lebesgue measure with measure of omega equal 1. We recall summary definition. Look at the screen. Important information about the symmetric space X has the fundamental function defined by equality. The fundamental function has many properties. Look at the screen. Important examples of symmetric space are the Lebesgue space LP, Orley space LH, Lorentz space lambda of psi, and Martinscapes space MC. Since them Lorentz and Martinscapes space will play important role in our construction, we present their definition. Look at the screen. Now we give good two-sided estimation of fundamental functions of grand and small spaces. These formulas are not only of independent interest, but can also be used to prove embeddings of grand and small spaces into symmetric space. We obtain good two-sided estimates of fundamental functions of grand space. Theorem 8 and theorem 9. Значит, we obtain good two-sided estimates of fundamental functions of small spaces using duality theorem. Ten and 11, and embeddings theorem 11 and theorem 13. The report is based on the article 1. The discussion of problem from my report can be found in the paper from the list of reference. Thank you for your attention. Sorry of my English.